Hello, everybody. Firstly, I want to sincerely apologize for being unable to attend the conference in person. Due to my visa issue and my advisor's health issue, we could not travel to Rome. We would like to thank the organizers for being considerate and allowing us to make a video presentation instead. I would now like to start my presentation regarding latency energy co-optimization for fog-based IoT services using HMP servers. In recent years, more and more IoT services from various sectors, such as manufacturing, home automation, and vehicular networks, are being hosted on the cloud. However, these IoT services must strive to co optimize latency and energy, that is, guarantee service level objective or SLO for end users' tail latency, and minimize server energy consumption for service providers. Future IoT services are expected to be even more latency sensitive, needing sub-second latency guarantees. Migrating them from a remote cloud to a nearby fog cluster can significantly reduce this user latency. Hence, fog IoT services seem to have a promising future. But fog IoT services present both opportunities as well as challenges towards co-optimizing latency and energy. Firstly, fog migration leaves larger headroom for latency for service response time, allowing room for longer services and more efficient scheduling strategies to be adopted. But service SLOs must also be recalibrated for the fog domain. Secondly, compared to cloud, fog IoT services endure reduced interference from co-executing workloads. But this also causes underutilization and hence energy wastage in traditionally energy inefficient server processors. Thirdly, fogs present opportunity for specialized hardware and software platforms suitable for specific IoT services. However, due to the small scale of fog deployment, cost effectiveness of such customizations are questionable. Finally, fog clusters witness significantly lower traffic compared to the cloud platform, thus eliminating network jitters and delays. But over a small scale, IoT services observe higher traffic variability too, and cannot exploit opportunities such as diurnal patterns to predict request load and maximize energy saving. In view of these facts, we believe heterogeneous multiprocessors or HMPs are ideally suited for hosting IoT services on fog clusters. HMPs are widely popular in mobile and SBC platform. A HMP consists of mix of big, fast and powerful cores and small, slow but energy efficient cores. Due to their low cost and higher energy efficiency, they have a lower cost of ownership and hence are a lucrative choice for the fog servers. However, co-optimizing latency and energy requires efficient scheduling across big and small cores. Overdependence on small cores can save energy but can also build up queuing delays at moderate loads, thereby threatening SLO violation. Similarly, overuse of big cores can waste energy and latency headroom for the IoT tasks. Recent works have used more or less identical approaches to address this scheduling problem. Big cores are exploited during high loads to meet the SLO, whereas tasks are scheduled on only small cores during low load times to maximize energy savings. Cores have also been frequency scaled while processing IoT tasks to save further energy. The decision regarding which cores to host IoT services on is made at every sampling epoch. A tail latency metric such as P99 is calculated at every sampling epoch. P99 here refers to the 99th percentile response latency for a sample of tasks serviced within a sampling epoch. Based on the tail latency measured in the prior sample, additional or fewer cores are used in the next epoch. But prior works perform co-optimization only at a single server level. In a cluster, request load is distributed across multiple servers, And with the current approach, servers can only optimize energy for the load that each of them individually receives. In our work, we propose to fully exploit core heterogeneity and optimize energy at the cluster level. A HMP-aware load distribution across the servers can potentially optimize latency and energy for the aggregate cluster load. However, compared to the server-level scheduling approaches, this is much harder to achieve on real-life workloads. To solve this problem, we developed a smart cluster-level task manager called Greeniac. Greeniac consists of three components as highlighted in the figure. First, a two-level learning agent consisting of a centralized cluster-level agent or CL agent and multiple server-level agents or SL agents. Second, a centralized load balancer which distributes cluster load across HMP servers. And lastly, service schedulers at server level to distribute requests across the HMP cores. Now, let's see how these three components perform the cluster level co-optimization. Greeniac's learning agent uses a special type of reinforcement learning or RL technique called multi-armed bandit or MAB. Using MAB, they explore various possible HMP core combinations and learn the most suitable set of cores to employ for a given load that co-optimizes energy and tail latency. Firstly, a single SL agent is initiated on one of the HMP servers. Since identical HMP servers have identical characteristics, Greeniac performs learning on a single SL agent, thus allowing other servers to continue processing real traffic. Only a controlled traffic load is forwarded to the learning HMP server. Using the service scheduler, SL agent explores various scheduling choices, that is the set of the cores to host services on. Based on latency and energy metrics calculated at the end of a sampling epoch, SL agent learns how good a scheduling choice is. After sufficient exploration, SL agent learns which scheduling choice performs the best co-optimization for a given load. As mentioned in paper, we used several heuristics to significantly speed up this learning process. The learned information is then relayed to the central CL agent. This information consists of a list of optimal HMP configuration corresponding to every load range. The list is then broadcasted to the SL agents on other identical HMP servers. The CL agent then performs the next phase of learning by exploring the various combinations of optimal HMP configurations and load distributions. Post-learning, CL agent identifies the optimal load balancing ratio and cluster-wide HMP scheduling for a given cluster load. At every sampling epoch, it directs the load balancer to proportionally distribute the load across the HMP servers in the optimal ratio. It also directs each service scheduler instance about the set of the HMP cores to use. The service scheduler then sets up the desired frequency on target cores and spawns IoT services on them. Subsequently, incoming requests are distributed among the active cores on a first come first served basis. Greeniac strategy has several strong and weak points. One of the biggest strengths of Greeniac is that it can learn online while still guaranteeing latency objectives. The heuristic-based RL approach enables significantly faster learning compared to the traditional RL approach and does not require a special training phase. Due to its service-agnostic nature, Greeniac can optimize most IoT services. Also, the two-layer learning approach can enable optimization on the heterogeneous clusters consisting of different types of HMPs. But the coarse granularity of learning, tail sampling, and configuration updates leave a lot of room for further energy saving. Furthermore, potential interference effects from co-executing applications have not been considered by Greeniac. Scalability of CL agent learning on large clusters is also a concern, but such issues could be addressed through divide and conquer strategies. For our experiment, we calculated real system power and latency results for the Lucene workload on Xeon and Atom processor-based servers. We developed an in-house simulator based on discrete event simulation and instrumented it with our measured experimental results. We performed simulation on a small 4-server cluster for most of our experiments. The request traffic was Poisson and the service time distribution was log normal. Now let's look at some of the results. Since Greeniac performs cluster level load distribution, we compared it against two of the most used cluster scheduling techniques. Least loaded represents an equal load distribution across the HMP servers in a cluster, and bin packing tries to use minimum number of servers for a given load by maximizing utilization on the active servers. For a fair comparison, we enabled HMP-aware scheduling on individual HMP servers for both least loaded as well as bin packing. Our results showed that Greeniac can achieve up to 30% more energy saving over the best performing competitors. Also, the majority of gain is achieved in the lower middle load range, which is also the typical operation range of most clusters. To study scalability effects, we executed Greeniac on 4 different cluster sizes. In this plot, dots represent the 95th percentile latency and lines represent the aggregate cluster power consumption for various cluster load ranges. The dotted line represents the SLO target of 1 second. The number in the parentheses represent the cluster sizes. As observed in the figure, Greeniac guarantees the SLO and achieves optimal close to SLO tail latency. We also observed that for any given load, aggregate core power consumption reduces with increase in cluster size. This is because in larger clusters, Greeniac learns to use more small cores and fewer big cores to achieve greater energy saving. Different types of IoT services can also have different service time distributions. We tested two types of services with same mean service time. The one in red has lower standard deviation, whereas the one in blue has wider variability in service time. As observed in the plot below, the blue dots end up violating tail latency at relatively lower load. Also, the blue line ends up consuming significantly more energy compared to the red. This is because wider service time variation can cause head of the line blocking by larger requests and thus potential SLO violation at even lower load. However, Greeniac learns to adapt to such services and employ more bigger codes to meet SLO requirement, although at higher energy cost. We also explored how Greeniac fared with optimizing cluster scheduling for different application characteristics. For this, we tested 3 different types of service applications with identical service time distribution on big core. The histograms on the top denote the service time distribution for requests serviced on small cores. Application A in blue is our default application. Application B in red is a relatively memory intensive application and thus displays a lower standard deviation. Application C in orange is a relatively CPU intensive one. The small cores take longer to service the request and have a higher standard deviation. The plot below shows the cluster power as lines and P95 latency as dots. We observe that the orange line representing CPU-intensive application consumes higher energy, whereas the memory-intensive task in red consumes the least. This is because GreenEAC learns to employ more bigger cores for CPU intensive tasks and fewer of them for memory intensive tasks. Due to the longer service time on small core, application C has a longer mean service time too, and thus ends up violating SLO at the relatively lower load. This is opposite for the memory-intensive application B, which could be sustained for further higher load while consuming lower average power for the cluster. To conclude, we suggest that HMPs present great energy saving opportunities for fog IoT services. Our proposed manager GreenEAC leverages cluster level HMP aware load distribution to gain up to 30% energy saving over server level HMP aware scheduling techniques. GreenEAC enables higher energy saving for larger clusters and can adapt to various IoT service characteristics. Thanks for attending the talk. Please feel free to contact us for any queries or further details regarding the paper or GreenEAC implementation. Thank you and have a great day.